Okay, so welcome everyone to Guided Study Group Week 10 of Statistic 100. So as I mentioned last Thursday, this week today is going to be the midterm 2 review for Statistic 100, and so there will not be any sessions this Thursday, only this sessions, and then I'll see you the coming Thursday. So for midterm 2, we have the main focus be the lessons from lesson 6 to lesson 9. So here the thing we have already learned in lesson 6 to 9, and I'm just going to briefly go over one of them, and I would highly recommend you guys trying to do your own review and maybe make your own notes. And also have a look at the cheat sheet that available on Canvas. So those are the information is going to be available for you during the actual exam. So make sure that any information that's not in there has already been noted and you already review them so that you have them in mind when you do the exam. So the first one is lesson 6. It's where we deal with correlations, linear regressions. So correlations shows how close the values that we have in the data set that forms to a straight line, including the strength and the directions of the relationship between the two variables. Correlations usually represented by R range from -1 to 1. And an important thing to note is that it depends only on the standard score of each variables and not on things like the unit of the variables. If you change the units of the variables, the correlations do the same, because it only shows if the variables are directly related to one another and if it's strong, medium, or weakly related to one another. Correlation is a descriptive statistic and is sensitive to outliers. Just kind of like a way that statistical software calculate the correlations is that they calculate it from all of the data points in the set. So it is descriptive because it shows like one of the summary of the data set, and it also is sensitive to outliers because it includes all the variables in the data set. We also learn about linear regressions. So after we calculate correlations, and if that is enough to conduct the linear regression showing the linear relationship between the two variables, we have the equation of a line b y equal ax plus b. When I did these sections individually, I put it at y equal a plus bx, but this is essentially the same. It's just the exchange of the variables. As long as you remember anything that relates to x, so the coefficient in front of x is the slope of the line, and a constant stand on its own is the y-intercepts. And so the slope is defined as the change of y with respect to 1 unit increase in x. So that's the slope, and the y-intercept is where you have x equals 0. We also need to, this is one of this equation of the line is used as is used to predict a value of y using a given x. So if they ask you like things like, they give you an equation of quiz score is equal something of homework score, then they ask you to predict the quiz score for a student that get maybe like 10 on homework score. So that's when you're gonna plug in x equal to 10, or like the homework score be 10 into that to calculate the quiz score. Linear regression also need to take point on the physical interpretation of the slope and y-intercept, because the slope is the change of y with one unit increase in x, and the y-intercept is the one that defines the y value when you have x equals 0. And so depending on if x equals 0 is included in the data set, that the y-intercept will have some physical meaning, because when x equals 0, not included in the data set, we cannot extrapolate and say that that means that when you have, say, thing like 0 homework score, then you're gonna have some quiz score, and that is not right. To physically give a meaning to the y-intercept, we need x equals 0 to be in the data set. The problems with correlations and regression is that, as I say, the x equals 0 is one of the example for extrapolation. So when you have some values that's not included in the data set, it might falls out of the linear relationship, and you cannot use the equation to extrapolate, or like plug in x equal that equation and just make a prediction, because it has to be in the data set. Correlation is not causation. So the correlation only shows the relationship between the two variables, but it doesn't give a meaning, say one will cause another. It just give a meaning that one increase might have some relations with the increase or decrease of the other. And finally, it's the illogical interpretation of y-intercept. So as I mentioned, when x equals 0 is not included in the dataset, you cannot give a physical meaning to the y-intercept. Then we have lesson 7. So lesson 7 deal mostly with open ups like the main materials on probability, odds, risk, and one important point is the Simpson's paradox. So the odds of an event is defined as the number of proportion with the trait and the number of proportion without the trait. And so we also have some things called the odds ratio. It's defined as odds of event 1 divided by odds of event 2. And one thing to note about that is that the odds ratio stay the same regarding the variable that you condition on. So say if you condition it on the explanatory variable or the outcome variable, the odds ratio stay the same. We also have risk. The definition of risk is the proportion with the undesirable trait. So make sure that when you read the questions, you know what trait the question is asking you for. Sometimes it's the undesirable trait, and sometimes it's the desirable one. Then we have relative risk. So the relative risk is, and the increased risk as well, is are the two values that we have to conduct based on the 2x2 table to compare the risk between different groups or different situations. So relative risk is risk of event 1 divided by risk of event 2. And so that's how we compare it. And usually it's in the form that if you see the sentence of like someone is more like how many times more likely to, catch that thing, then that the times sometimes more likely or less likely, then that's the relative risk. The increased risk is going to be relative risk minus 1 multiplied 100%. Note that in the risk comparison, beware of the baseline and how the risk relates to you. So sometimes people think of the risk like, even if it's just like 1 or 10%, people start to freak out and change their behavior based on that risk and the trait. But sometimes they haven't thought about the fact that if that risk is really related to you, like it's that undesirable trait or outcome, really relates to what you're doing, and also the baseline. So if you want to compare the risk, the baseline will, show you if the risk is significant or not. And so that one you can have a look back at lesson 7 examples, where you can see how the baseline will actually determine how big, how significant is the risk is for each outcome. And then finally, we have the Simpson's paradox. Simpson paradox saying An observed association between two variables can change or even reverse directions when there's another variable that interacts strongly with both variables. So say one of the most representative examples is like when you have male score higher than female in physical education class in one school, and also male and the same event happen in another school. But then essentially when you take the number from both schools, female actually have a higher, you know, score or like performance on in physical education compared to males. So that's one of the examples that we can think of for Simpson's paradox. You're gonna see that more if you do the practice problems on Canvas for exam 2. Now it comes to lesson A. So this is mainly talking about probabilities. And so we have 5 probability rules. The things that we need to remember is that probability has to be between 0 and 1. The outcomes, say if you're looking for the probability of some outcomes, and so it's gonna be equal to the probability of at least of each of the outcomes if they cannot happen simultaneously. And then we have the change of something is equal to 1 minus the change of the opposite things in case that we can only have 2 possible outcomes. Also, we have the definition of independent events. So independent event is defined as the probability of one event happen doesn't affect the probability of another event. If 2 events are independent, then the probability of the outcomes of both happening is going to be found by multiplying the change of each of them. And then finally, from number 2 as well, when you have if the ways in which one event can happen are a subset of the ways that a second event happen, then the first event cannot have a higher probability. So that's the 5 rules of probability. Then we have also mutual exclusiveness concept and how to do simulations for probability. So mutually exclusive events are defined as 2 events that cannot happen at the same time or in the same trial. Say if you throw a dice, a 3 off and a 4 cannot happen at the same time. You can only have one number in each row of the dice. And to simulate the probability in reality. So in reality, sometimes it's not that easy to just determine the probability of something happening. And so to do that, people tend to repeat a lot of trials with the same basic process. But to do that, they have to have a probability model that have the chance of each outcome happens similar to the problem that we're talking about. So say if the problems have 8 possible outcomes, your experiment or your simulation model has to have the same number of outcomes, and it has to follow kind of like the same mechanism as the problems that we're talking about. Then two last point in lesson 8 is where we have expectations and the law of large numbers, which also carries over to lesson 9. Expectations and expected value. So the expected value is defined as the long run average value of a measurement, and we do that by taking the sum of the outcome multiply the probability of each outcome. So say we have n outcome, and so we have to sum over the possible values times the probability of getting that value. And finally, we have the law of large numbers. So the law of large numbers says the average of proportions are likely to be more stable when there are more trials, while sum or counts are likely to be more variable. This does not happen by compensation for a bad run of luck, since independence independent trials have no memory. And so that's similar to the one that we said earlier. Where you have independent trials, knowing one happened doesn't affect how the other happened. And if you already have like 10 of the same outcomes going on, it doesn't affect um, the likelihood of happening or the outcome of the next trials, because each of the trials are independent. Um, yeah, average proportions are likely to be more stable. So when you take more trials, we have more values in the data set, and there's a higher chance that those data set really um, resemble the actual data points in the population. So it's more likely that we're gonna, when we calculate average or proportions, it's more likely to, get closer and closer to the reality. Then lesson 9 is the law of large numbers, and we discussed last week that there's no law of small numbers. So you cannot just base on some anecdotes, coincidence, or you know to generalize the big pictures of the populations. We also have sampling distribution of a summary statistic and normal approximation, which is a very important part of lesson 9. So sampling distribution of summary statistic. So say if you have a sample and you're trying to find a distribution of the average of that sample, it's where we take samples of a smaller size and calculate the average from that and just repeat that process like 5,000 times. Essentially, we're going to have a distributions. And so that distribution usually is going to look more like a normal curve if it's about average or proportions. And it has to come from a large number of independent trials. Then it's going to follow the normal curve. The expectation of a sample proportional average is its corresponding population value. And so that also coming from the fact that we have a large number of independent trials. Then we have two formulas to find the standard deviation of a sample mean and of a sample proportion. And so that's everything I have for the materials of lesson 9. Here's it just gonna cover the main points. So the main studies still come from your own review of the material, because you know best of what you're missing in the materials. And again, if you listen to this during the week and try to study for your exam, please let me know anytime through email or anything, that if you have any questions. So now we're gonna have some practice problems and questions that I took from the practice exam. I did it myself this morning, and I try to pick the questions that I got wrong on this, and I think it's gonna be significant for you guys to work on. So the first question, again, mute me if you want to work on it on your own. The normal approximation for the sampling distribution of the mean will work better when a population's histogram is symmetric than when it is heavily skewed. And so this one is coming from the first thing of normal approximation and what we talked about in the last lesson and in the last Thursday. So normal approximation works better when the original populations follows the normal distributions. If it fits better with the normal distribution, then the normal approximation will work better when you do sampling distribution of a summary statistic. And so A is true based on what we talked about last week. Now the next one, the normal approximation for the distribution of a sample proportion will work better when the true proportion is closer to 1. So the true proportion is when it's closer to 1. Then we have P is going to equal 1, and so standard deviation is going to be 0, because it's going to be 0 multiply 1 divided by the sample size. And so I think we have a small discussion about this. When normal approximation applies for proportion, is where the true proportion goes closer and closer to 0.5. And so for this one is false. And you can have a look back at lesson 9 or email me if you have questions on this one, because I notice a lot of people won't know this one either. 2.5 instead of 1. Now it's a second questions. Again, mute me if you have any problems with this. If you want to work on it alone, and listen to mine if you have problems with that. Overnight packages shipped by FedEx to one city weigh an average of 5 ounces with a standard deviation of 6 ounces. One package is randomly selected. The distribution of its weight is most likely to... Okay, so you have average of 5, standard deviation of 6, and you have one package. One package only. So n is equal to 1. Sample size 1. And so standard deviation and of the sampling distribution or of the population is the same, which is 6 ounces. What is the answer for this? And so we have mean here. Mean is smaller than the standard deviation. And it has to be all of the values. So all of the values in the data set, so all packages have to have positive weight. And so we have the distribution is going to be, so say this is the mean, and if we follow one standard deviation, it's going to be really far from, and it can't even get to negative. So to do that, it has to be positive, and so our population has to be skewed to the right. And so, alright. Okay, so that's why we have to be skewed to the right for the populations. And it's not that heavily skewed, it's just maybe like likely on the... This is because we discard this part of the populations, and so it looks likely skewed because we have this bunch. It cannot be negative, and so this is the populations how it actually look like, because we actually disregard a part of the population that is negative. And so we said it's skewed to, it's not skewed to the left, it's skewed to the right. Alright, now it comes to the next questions. Again, mute me if you want to work on it on your own. 20% of the cars in Wheaton, Illinois are green. An observer stands at the intersection of Butterfield Road and Park Boulevard in Wheaton for an hour and sees 898 cars traveling along Butterfield and 243 cars traveling along Park. In which direction is it more likely that between 15 and 25% of the cars seen will be green? A. It's more likely among the cars traveling on Butterfield, and B. more on Park Boulevard, and C. is just as likely among either two groups of cars. And so if we look at what the question is asking here, in which direction is it more likely that between 15 and 25% of the cars? So basically it's asking in which directions that the percentage of the car is closer and closer to 20 or within this part. And so as we learned last week, we have the law of large numbers. Average proportion is more likely to hold stable when you have a large number of independent trials. And so in that case, it's more likely to happen among the 898 cars traveling on Butterfield Road. And so A is the answer. Now, it comes question 4. We continue to use the scenario in question 3. Suppose that you watch 20 cars in a row traveling along Butterfield Road at this intersection and not a single one is green. What's the probability that the next car will be green? And so this one comes from the law of probability. So each of the individual trials are independent. And so there's no compensation, and also we have a lot of cars going on in this intersection, so there's no compensation for a bad run of luck because each trial is independent, and so the probability is not affected by what just happened, and so the probability of a car appearing in green is still the same and it's 20%. Now in doing that, we make the assumptions that the colors of the different cars we assume that colors of the different cars are independent of one another. Now it comes the last questions. Again, mute me if you want to work on it on your own. The distribution of the amount of soda that a customer buy at a customer buying a medium drink takes from a safe serve soda machine is skewed to the left. So skewed to the left, and so this is how it's gonna look like. Because they cannot take more than 14%, so we're gonna delete this part that's more than 40%. What can we say about the average amount of soda that will be taken by the next 200 customers using the machine? And so what happened is that we're gonna take samples from the purchase of the next 200 customers, and we're gonna take the average of each of those small samples, and then we're gonna construct a distribution. And so that's what we call sampling distribution of a summary statistic. And in this case, it's the sampling distribution of an average. And so based on that, we say that it's gonna look more like a normal curve when we have a large number of independent trials. And so we have the distribution of the average amount. A will look a lot like a normal curve. That might make sense. Let's look at B. We'll look skewed to the left since it will mirror the population histogram. Well, this is correct when you have smaller samples. Here you have 200, and so it's not really right. So I would thinking about excluding B first. And C, the distribution of the average amount will have a larger standard deviation than the amount taken by one customer. And so we have standard deviation be the actual standard deviation divided by the square root of the sample size. And so the larger the sample size, the smaller the standard deviation of the distribution of the average. And so C is also wrong because the standard deviation of the one customer is has the larger standard deviation than the standard deviation of a 200 customer sample. And then finally, the distribution of the average amount will have a larger mean than the median amount taken by one customer. So we have the mean of them is mean of the population is equal to mean of 1 and equal to mean of 200 because the mean is not depending on the sample size. However, when we have compare the mean with the median, for the original population, it's skewed to the left. And so in that case, it means that the median is going to be larger than the mean because the mean is affected by outliers. This is the median. And so all of them is going to be larger than the mean. And so D is also wrong because mean is not larger than the median. Oh, these are all smaller than them because the mean is not larger than the median. And so A is the right answer. And so if you have any questions when you listen to this recording at home, feel free to contact me and I'll be more than happy to answer your questions. Now, final notes. The next review is not going to be on this day, but it's going to be, so next week is going to be 23rd, 24th, 20. So it's gonna be July 26th, 10 p.m. Eastern time, and we're gonna work on the materials for the final exam. If you have any questions, again, email me. If not, good luck with your exam, and I'll see you guys in 10 days. Thank you and bye.